people. I hope we're doing well today. In the last video, we simply looked at a function and being asked to take the area approximations on a particular interval, given successively doubling the number of subdivisions and showing in a pictorial and graphical way that each successive addition of more and more subintervals will increase or decrease the error of the approximation and increase the worth of the approximation, how close it is, right? So we're going to start doing the calculations, start actually getting a value for these. And for the next couple, we're going to talk about this particular function, f of x is equal to 9x minus x cubed. Okay? Now, when we're talking about these sums, they go by a particular name, and I think you probably picked up on this already because of the name of these videos and the playlist. They're named after a German mathematician named Bernhard Riemann. And if you're curious, that's what he looks like. A handsome fella. He was a 19th century German mathematician, one of the most prominent in the history, especially of the West. And he was a student of Carl Friedrich Gauss, if that name means anything to you. And if it doesn't, we'll get into a little bit about him in one of the future videos. But we're going to be entertaining this particular function on the interval 0 to 3. Okay? So actually, in this particular case, it's going to go from 1, 0 to the next, and we're going to be doing it with 6 subintervals. So we're going to be carving them up every half unit. Okay? And over the next this video, we're going to be dealing with one particular type of Riemann sum, and what we're going to be talking about here are right-hand Riemann sums, which basically means I'm going to be calculating the height of the rectangle for the particular subinterval based upon the function value on the right-hand side. Okay? And so let's actually go ahead and take a look at this function. This is still the same function, f of x is equal to 9x minus x cubed. And we're going to carve it up, and we're going to basically use the right hand. So if we go here and come down, we recognize the fact that this is right hand for this first subinterval right here. Okay? I'll go ahead and just draw the bottom for the whole thing. If we go up, this is the right hand function value, and therefore determining the height of this subinterval. Okay? And this is determining the height of this subinterval. And this is determining the height. And those aren't identical, but they're close enough to where with a broad drawing highlighter pencil, these two look the same, right? And so we're going to get that. And then we get to this last subinterval, and you think to yourself, but the function value on the right-hand side is 0. Okay, well then you have a rectangle with a height of 0. And I don't know if it's necessary to actually color these in. I think it actually makes it a little easier to look at, right? And then you need to ask yourself every once in a while you need to ask yourself, is this an overestimate or is this an underestimate? And this one, it's actually kind of difficult to tell because here you have it being under, and this is under, and this certainly under. But on these three intervals, it's over, over, over. And how do those balance out? Well, I don't exactly know, but let's go ahead and let's actually calculate it out. And what we really need, since all of these are of uniform width, and we'll eventually get to ones that don't have a uniform width, but because all of these are uniform width, they all will have the same width, which is of course 1/2 of a unit, because you've taken a full interval, which is 3 wide, and chopped it up into 6 equal pieces. The math is not difficult, right? And so our area will be And for that first rectangle, it's going to be a width of 1/2 times f of, well, the height is determined by the function value at 1/2, f of 1/2. And again, the second one has a width of 1/2 and the function value here at f of 1 times f of 1. And we'll just keep going. 1/2 times f of 3/2, and then 1/2 times the function value at 2, and then 1/2 times the function value at 5/2, and then 1/2 times the function value at 3. Now we already know that the function value at 3 is going to be 0, but I just wanted to list all of them out. Okay. So since they all have a uniform width, you can actually just factor the 1/2 out in front, right? That winds up basically being functionally a greatest common factor. I mean, not just functionally, it actually is a greatest common factor. And so my area, approximation at least, is equal to 1/2 times that function value at 1/2 plus the function value at 1 plus the function value at 3/2 plus the function value at 2 plus the function value at 5/2 and plus the function value at 3. And now what we need to do is actually calculate those function values. And you get 1/2. And this is where it might get a little bit cumbersome. But you have 9 times 1/2 minus 1/2 cubed, right? And plus 9 times 1 minus 1 cubed. And that, of course, is your f of 1. Your f of 3/2 is 9 times 3/2 minus 3/2 cubed. And your f of 2 is 9 times 2 minus 2 cubed. And your f of 5/2 is 9 times 5/2 minus 5/2 cubed. And your f of 3 is 9 times 3 minus 3 cubed. And that winds up being how you calculate it. Now, I could break out the calculator and show you right now, but let's go ahead and I'm just going to spoil the surprise on some of these and save us a little time. That first one right there becomes 9/2 minus 1/8. That becomes 35/8. That becomes 9 minus 1, or 8. That becomes 27/2 minus 27/8, and that winds up being, or plus, minus, so 81/8. So 27/2 minus 81/8, or 27/8, winds up being 81/8, okay? And then you get 18 minus 8, which is 10, and then you get 45/2 minus 125/8, which is 55/8, and thankfully a lot of these have a common denominator, and 0, and what winds up happening is you wind up getting 1/2 times 315/8, and that winds up being 19.688 approximately to 3 decimal places. And that is how we work it out numerically, right? And that is the approximate area under the curve for that function on the interval from 0 to 3 for 6 subdivisions. I mean, it's very specific, okay? So what we want to do now is take this example and actually start working some more examples a little bit quicker, and I'll break out the calculator here in just a second, okay? So let's take a look at this one. Now let's talk about the notation first of all. This R right here obviously refers to a right-hand Riemann sum, and the subscript is telling you how many subintervals you need to use. So we're doing a right-hand Riemann sum of 6 subintervals for the function f of x is equal to 1 over x minus 1, x times x minus 1 on the interval 2 to 5. And I provided the graph right here, and I've even provided vertical lines here at x is equal to 2 to 5 in order to sort of make very, very clear what interval you're looking for. So you're looking for the area under the curve, but we don't know how to do that just yet. So we're going to look for the approximate area under the curve. Again, 6 subintervals over 3, so each subinterval is going to be 1/2 unit wide. And I'm using the right-hand function value, so so we'll basically, at every function value, we'll draw our little height, our top of the box to the left, top of the rectangle to the left. And these are going to get a little bit, with a highlighter pencil that's so fat, these are going to start to sort of look indistinguishable from one another. But I also need it to be able to show up on the video. So there's also the reason I use pink. A lot of the other ones, for some odd reason, for the video camera or the recording software that I use, just don't show up. Okay, so we're looking for that. Now obviously this reveals something very important. Now you don't have to actually memorize this, but conceptually it's pretty important to understand. On the interval, the function is decreasing over the entire interval. Okay, if you use a right-hand Riemann sum on a decreasing function, you're going to obviously get an underestimate. If you used a left-hand Riemann sum on this decreasing function, you would obviously get an overestimate. And you can sort of flip that logic for something that is increasing on the entire interval, and we'll deal with one like that shortly. Okay, but let's go ahead and actually do the arithmetic. Let's actually do the evaluation. And we know that our area, and when I put area right here, obviously I'm talking about the area approximation, the area sum of those rectangles. I know that that first rectangle is 1/2 times the function at, well, if this is 3, 2, 3, 4, and 5, at 2, this is going to be 5/2, this is going to be 7/2, this is going to be 9/2, and I can use those as my inputs, right? Because I need 1/2 times f of 5/2. And here's the thing. I already know that all of them are going to have this 1/2 out in front, so I'm going to save myself a little bit of time and just in my head factor it out, and then just put the sum of all of the heights, all of the function values. F of 3, f of 7/2, f of 4, f of 9/2, and f of 5. Now, what that really looks like in terms of actually working this out, and it's nice that this is in factored form, that's really 1/2, 1 over 5/2 times 5/2 minus 1. 1 over 3 times 3 minus 1. 1 over 7/2 times 7/2 minus 1. And 1 over 4 times 4 minus 1. And 1 over 9/2 times 9/2 minus 1. And 1 over 5 and 5 minus 1. Now that still looks a little bit ugly, so I tell you what, let's actually do this one with our calculator. So let's go to our y1, and let's go ahead and plug in, let's create the fraction, 1 over x times x minus 1, and then let's actually go to the home screen. Now I want to recreate this right up here on the home screen, because remember, if I plug something into y1, I can actually use my home screen to evaluate the function value. Now, you can either put the 1/2 in there and put parentheses and try to keep track of that, or you can just do the function values and just remember to divide by 2. Whichever one you think is going, are you more likely to make a forgetfulness error or a keystroke error? That's really kind of the determining factor of how you do it here. So let's go y1 at 5/2, right? y1 at 3. y1 at 7/2, which is 3.5. y1 at 4. y1 at 4.5. And y1 at 5. That's going to give me 0.74 repeated, and that of course is double the answer that I'm looking for. And what I am actually looking for is the approximation. And in case you're curious, you could actually work this all out, and it winds up being 1/2 over 67 over 90, which is 67 over 180, which, surprise, surprise, is 0.372. And the 2 is repeated, but as always, we ask you to approximate to 3 decimal places. And that is the area approximation under the curve. And because it's a right-hand Riemann sum, and it's a decreasing function over the entire interval, we know that it's going to be an underestimate. We know that the actual area is going to have to include all of these little green pieces right here that basically the rectangle's missed. Okay. Alrighty, let's do another one. Now this one, let's look at the notation, is asking you for a right-hand Riemann sum with 4 subintervals on the interval from 0 to 2, which again, and you know, you're going to wind up with a lot of these where the width is a very consistent 1/2 or 1/3 or 1/4 or even just 1, okay? So just make sure that you're a little bit careful in remembering to sort of calculate that. But basically what that means is if this interval is too wide and I'm looking for 4, I simply need to, you know, figure out what's halfway between 0 and 1, because that right there is 1/2 and that right there is 1 1/2 or 3/2. Alrighty. Now again, we're using a right-hand Riemann sum. By the way, just in case you're wondering, or just in case it's helpful, you're probably not wondering, putting it in that form might actually be helpful here before long. If you want to leave it in the unfactored polynomial form, by all means, go crazy, okay? But let's go ahead and actually draw this. Now we know that that function value right there, since it's a right-hand Riemann sum, is going to determine the rectangle to its left, okay? And the same thing with this function value. So I guess that second subinterval actually is just 0, okay? And this should be the same height as this one because of the symmetry around x is equal to 1, but again, you know, fat pencil. But as long as we get that correct when we actually do the calculating work, then of course we'll just recognize the fact that our drawing is just meant to be a helper, not meant to be precise. Okay, and so what we have here in terms of a right-hand Riemann sum is this. Now, it is not totally increasing, it is not totally decreasing, it's doing a little bit of both over the interval, so it might be a little bit difficult to determine whether this is an overestimate or an underestimate, but let's go ahead and keep going. Now we recognize the fact that our area, and by this of course, again, I mean my area approximation, the sum of the rectangles, not the actual area under the curve. If I'm talking about the area under the curve, I'll have to do the squiggly equal sign to show approximation. So I have 1/2, which is that consistent uniform width of all of these rectangles, right? And of course, because that is consistently the width, I'm going to factor it out and then evaluate f of 1/2, f of 1, f of 3/2, and f of 2. This one is actually really easy, not nearly as difficult as the last one in terms of evaluation, because especially in this factored form, I can just plug in, well, what's 1/2 minus 1? Negative 1/2 squared is 1/4. What is 1 minus 1? 0. 0 squared is 0. What's 3/2 minus 1? 1/2. 1/2 squared is 1/4. And what is 2 minus 1? 1. 1 squared is 1. Now what is 1 plus 1/4 plus 1/4? It's 1 1/2, or 3/2. So this is 1/2 times 3/2, or 3/4, and that is my area approximation. But of course, you can, again, do it in terms of just plugging in here, x minus 1 squared. Okay, so if we have y1, plugged in accurately, and we go back to the main screen, then we can basically say, okay, well, y1 at 1/2, and y1 at 1, and y1 at 1.5, and y1 at 2. Oh, sorry, at 2. No, see, I messed up. Keystroke error, right? That became y2, so I need it y1 at 2. And I need to sum all those up, obviously, which I have on the screen. I was just failing to say that as I went. And that is 1.5, and you multiply it by 2, or divide it, and you get 3/4, which is exactly what we got here. Okay? Obviously, the calculator work is going to be much more important on those functions where you're going to get irrational f of x values for your height of those successive rectangles, those successive subintervals. And that we'll see that here in just a little bit. One more example of a right-hand Riemann sum before we bring this video to a close. We'll of course be doing left-hand Riemann sums on the next video. So this one is very similar to the last one, except for on the same interval, instead of being an upward-facing parabola throughout the interval, it's a downward-facing parabola. But we're still looking, oh, in this one it's actually 6 subintervals. I actually didn't read that before. I'll tell you what, let's just, actually, yeah, let's go ahead and do it 6. That looks good. And thankfully it's subdivided in such a way that makes it easy. Now sometimes those graphing programs don't really, oh no, that's going to be 5. I tell you what, let's not do 4 because that was boring. Let's actually change this to 5 so that we can actually do it easily on the graph. Sound good? Now this right here is going to be 2/5. This is 4/5. This is 6/5. And this is 8/5. And this, of course, right here at 2 is 10/5, which reduces. So let me go ahead and sharpen this pencil so I don't actually have to use such thick lines. All right. Hopefully that will do. Right-hand Riemann sum. So let's go ahead and go. So we're going to use this point and basically draw it to the left because it is on the right hand of this particular subinterval. Here, I'm going to draw to the left. Here, I'm going to draw to the left. And those are the same height because 4/5 and 6/5 is, they're basically symmetrical about this axis of symmetry through x is equal to 1. And we have here, and of course the right-hand Riemann sum of this last interval is going to be 0, right? Now, again, it's just fractions and squaring, so I could actually take this function, maybe put it into vertex form to make the calculations easier. But just to reinforce how the calculator helps us on this, we're going to do this one with the help of the calculator. But let's go ahead and actually show analytically what the area should look like. So the area approximation, the sum of the subintervals should be, well, the constant width is 2/5, right? Because it's an interval that is too wide, broken into 5 pieces. At which point we're going to have, okay, well, the first subinterval is going to be determined by the function value at 2/5. The second subinterval is going to be, the height of it is going to be determined by the function value at 4/5. The third subinterval determined by the function value at 6/5. The fourth subinterval, in like fashion, determined by the function value at 8/5, and the last one, the function value at 2. Alrighty. Yeah, this is going to be a little bit cumbersome if we actually have to deal with those fractions and squaring and all sorts of fun stuff like that and changing the form of the function. And plus, every once in a while, it's nice to sort of go to the calculator and remind ourselves that even though sometimes we don't need it, for the times that we actually do, let's go ahead and actually, explore how it actually does the work for us or helps us in these regards. Our f of x is in our y1, so I need y1 at 2/5, and if you want, you can use the decimals just for the ease of keystrokes, right? So that's 0.4, and then 0.8. And then y1 of 1.2, which is your 6/5, and then you need the y1 of the 8/5, which is 1.6, and then y1. Now, that f of 2 is going to be 0, but just for the sake of being exhaustive. And then, of course, we need a closed parens so that the whole thing gets multiplied by that fraction of 2/5 that I put out in front, and enter. And what I get here is I get an area that is 1.28, and the reason why it's 1.28 obviously is just we're using actual fractions and it's not irrational, and so it makes sense that it could potentially sort of end before that third decimal place that we usually use for approximations. Okay, If we had done it with 4 subintervals, I actually had it worked out with 4 subintervals because I didn't read the 5, we actually get 5/4, which is 1.25. This is 1.28, very, very close, okay? This brings us to the end of our second video. Like I said, in the next video, we're going to be dealing with left-hand Riemann sums, and in the fourth and final video of this playlist, we're going to be doing what are called midpoint Riemann sums, where you actually take the function value from the middle of each subinterval to determine the height, and we're going to look at what that looks like. So be on the lookout for that. Bye.